Welcome to period 2 on January 10th, 2020. We're going to be talking about empirical formulas today, and I'm going to show you how to solve an empirical formula here. And I'm going to use some examples right from the book. If I can get this open and this. Okay, now let me talk about why this is important in the first case. An empirical formula basically starts with something that looks like this. It starts with a percent composition, and our goal is to calculate what the empirical formula is. So a lot of times, here's what happens. This is popular in forensics, forensic medicine, or forensics crime scene stuff. Doctors use this a lot to figure out what kind of drug is in somebody's system, or when they're doing an autopsy, what might have killed somebody, if it's a drug or if it's something that's not supposed to be in their system. And so what happens is somebody finds a piece of something, they bring it to a lab, and they put it in a device called a mass spectrometer. A mass spectrometer is a really big piece of equipment. It basically incinerates something, and then it analyzes the spectrums, the frequencies of energy that are given off, and it tells you how much percent of each element is in something. So you might get a report and say, okay, this was found at a crime scene, and it's 52% carbon and 18% oxygen and 3% arsenic or whatever, okay? And it gives you a percent composition like we did here. But you don't know what that substance is. So what chemists do is then they can take what we're going to do today, it's a mathematical calculation to take that percent composition and change it into an empirical formula. And once you have an empirical formula, you can look up in a catalog of molecules or a catalog of substances what that substance might be that has that empirical formula. Okay, so I'm going to show you how to do this. I'm going to use the problems right from the book in chapter 10, and then we'll do a couple from the end of the book in the supplemental section as well. Calculating an empirical formula from mass data. This is on page 349 if anybody wants to look it up later and see how the book solves it. I do this all in one big chart. This looks like a huge chart of numbers up here. I'm going to walk you through it. Please ask questions as we go. The book does it in a stepwise fashion, which to me is bothersome. But if it works for you, obviously I'm not going to lock you into the way that I learn how to do stuff. But I think my method is very concise, and I will explain it as best I can. Okay? But the book generally does things down a page, where I've got this nice piece of whiteboard behind me I can work on. The problem says you are given the masses of elements found in a known mass of ilmenite and must determine the empirical formula of the mineral. Convert the known masses of each element to moles. Find the smallest whole number ratio of the moles of the elements. Okay, so it says iron equals 5.141 grams. And titanium is 4.64 grams. And I know I have oxygen, 4.65 grams. Now in this particular case, this doesn't start with percentages, okay? So I'm going to show you one in a few minutes that starts with percentages. If you want to watch the video from first period, I did start with one that starts with percentages, and we didn't do this problem in first period. So you can watch both classes if you want to see more examples. Okay, the first step here is I need to change these to moles. We're always going to figure out how many moles of these are in grams, grams, and grams. Okay, so we're going to put the grams of iron per 1 mole, the grams of titanium in 1 mole, and the grams of oxygen in 1 mole. These are your molar masses, and this would be 16 for oxygen, of course. Iron is about 55.845, and I'm not going to round that one off for, you need to be careful on these, 55.845. I'm going to leave that one with the decimal for now. And titanium, 47.867. Okay, so the first step is grab your calculator, change all 3 of these into moles. So the next column is going to be the number of moles. So I've got the grams, I've got the molar masses, And then we're going to calculate how many moles of each of these. So 5.41 divided by 55.846. So 0.0969. I'm going to leave a few decimals here. In the middle of this problem, don't be worried about leaving a few extra decimal places. We're not worried about sig figs, remember, until we get to the very end of the problem. And in this problem, your answer is not going to be a numerical answer. So I can carry some extra sig figs here. It's not a problem. In the middle of this one, 4.64 divided by 47.867. 0.09. What? Isn't that interesting? Okay. And then the third one here is 4.65 divided by 16. 0.2906 if you want. Now, once you write that down, look up here for a second. What these three numbers tell me is the number of moles, if I wanted to label it, moles of iron, moles of titanium, moles of oxygen. This is the mole ratio. This is the ratio in which these moles combine to form whatever this substance is, ilmenite or whatever it's called. If I wanted to, I could actually do this, but I'm not going to because it'd be wrong. And I could write the formula, Fe 0.0969, Ti 0.069969, and then O 0.2906. Okay, now does that look really stupid or not? Okay, yeah. It should look like, whoa, you can't do that. Does everybody say that? Everybody say, whoa, you can't do that. Whoa. Okay, good. Because you can't do that. Those have to be whole numbers, right? I've drilled that into you. I hope your subscripts have to be whole numbers. This is true, but it's not a good formula because we always write formulas with whole numbers. So our goal is to change these three numbers into whole numbers. I'm going to show you how to do that in 2 easy steps, okay? These have to be whole numbers. The ratio of this to this is going to stay the same. Let's just draw a line through that. How do I do that? The first thing you're going to do is divide all of these numbers. There might be 2 of them, 3 of them, 4 of them, 5 of them, or more. You're going to divide all these numbers by the smallest of those numbers. In this case, it's 0.0969 is smaller than 0.29. So I'm going to divide all 3 of these. I'm just putting a slash to indicate division. And I'm going to write 0.0969, 0.0969, 0.0969. Now, at the very least, that will change at least one of these numbers into a 1, right? Anything divided by itself is going to be 1. So at least one of these will turn into a 1. And hopefully, some of the other elements will turn into whole numbers as well. You'll find it's magical how it happens, okay? This obviously is 1. And this one's also going to be 1. So I like this one. This problem is kind of cool. I got two whole numbers right off the bat. Now if I take 0.2906 and divide by 0.0969, ooh, I like that too. 2.9989. Which actually that 9 rounds up to 2.999. Does everybody agree that's really close to 3? Yeah. Okay? Like super close to 3, like 1/10,000th away from being 3. So we're going to call this 3. So the ratio, since I've divided all 3 numbers by exactly the same number, the ratio has not changed. The proportion has not changed. So my final answer here for my empirical formula is Fe, one of them, I don't need to write the 1, Ti, one of them, O, 3. FeTiO3. And that is my final answer. This is the empirical formula for ilmenite. Yeah, interesting. And it's the raw ore that titanium comes from. Really cool. Okay? Does everybody see what we did? Now the steps, every time are going to be the same. We're going to start with grams. We're going to change grams into moles. We're going to divide by the smallest number. If you want to write these steps down, that's fine. Okay, start with grams or get grams. change all the grams into moles, divide all of the moles by the smallest number, and then you're going to look at these numbers. Now, sometimes there's going to be an extra step. I'll do another problem for you that shows that last step. This one came out to be 3 whole numbers, 1, 1, and 3. Boom, we're done. Okay? This is the empirical formula. I'm trying to remember which one I did last period. Okay, let's do another one. Any questions here? Everybody understand the steps? There's nothing that we haven't done. We know how to change grams into moles. And then the other 2 steps, just divide by the smallest number and look at these numbers and figure out if they're whole numbers or not. The next one is on page 348. Again, if you want to look it up later. This one actually starts with a percentage composition. I'm trying to figure out something that has 40.68% carbon. It has 5.08% hydrogen. And it has oxygen 54.24. So this is a compound we're looking for. It's called, assume you have a mass percent. You can compare the molar mass, blah, 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 use the percents. Okay. So here's my percentage. A lot of these problems are going to start with percentages. Here's the first step. Now this was not on the previous problem because we started with grams on the previous problem. The first step is to change this into grams. If I assume a 100-gram sample, which is fine, okay, it doesn't tell me how much I have, it just tells me the percentages. Then everybody tell me, what's 40.68% of 100? 40.68, okay? So if I assume a 100-gram sample, it tells you to do this in the instructions on this problem, which is kind of cool, then that changes to 40.68 grams. No kidding. What's 5.08% of 100? 5.08 grams. And what is 54.24% of 100? 54.24 grams. So what you'll see is that if they give you a starting point of percentages, you can always just change them into grams automatically. True?
Oh, why'd you do 100 gram? Like when it says the molar mass is 118 grams. It says the molar mass.
Yeah. We don't need to know that. I'm not going to. I'm going to.
So you're just saying that you can change. If you get a percent, you can just change it.
Yeah. The molar mass is used at the end of this problem to calculate what the molecular formula is.
Okay, thanks.
So it's unrelated to this. Okay. We're going to assume a 100-gram sample all the time. If we're given percentages, we're going to assume a 100-gram sample. In this case, back here, I didn't need to do that because I was already given grams. If I'm given grams, just dig right in and start changing the moles. If I'm given percentages, you can just write down the number of grams, because if you assume a 100-gram sample, it's not going to change any of the numbers. Now we're going to do the exact same steps we just did on the last one. Change this to moles, change this to moles, change this to moles. Okay? So, grams per mole carbon, 12. Okay? If you don't have to memorize carbon, hydrogen, and oxygen yet, you haven't been doing homework, because there's a lot of carbon, hydrogen, and oxygen compounds in the world. Carbon is 12, hydrogen is 1. Oxygen is 16. And we're going to get 3 numbers here that is going to show me the ratio of moles to each other in this compound. 40.68 divided by 12. 6.389. 5.08 divided by 1. I always do that. I hate doing that. Okay. And 54.24 divided by 16. That doesn't look right. 54.24 divided by 16. 3.39. Each one of these is in moles. Moles of carbon, moles of hydrogen, moles of oxygen. No.
The top one is wrong.
Yeah, it is. It's got to be 4 point something.
Yeah, 3.39.
Yeah, it is. Ooh, that works out nice. There's another one. So I like it when I see things that kind of look like they're going to be easier. That's the same as this one down here. This means those subscripts are going to be the same number. Very cool. Okay. Yeah.
For hydrogen, what is that? Let's say 1 or 10.
1 gram per mole. 1 gram per mole. Okay.
Okay, so in the book it says, like the top one, it says 3.387. Can we just round that to 3.39 if one's kind of close to it?
You need to be careful. On these problems, if you round off a whole bunch, I'd rather you not round anything off on some of these because you can get to the end of these problems, they're so long, and have something that you can't figure out because you do too much rounding off. So if you have a choice, don't round off. I do a little bit of rounding off because I can always look in the book and see the answer. But what's the next step? We're going to divide all 3 of these by the smallest number, 3.39 in this case. 3.39, 3.39, 3.39. Now it's obvious that the top one and the bottom one are going to change into 1s, and the middle one we'll have to see. It's definitely not going to be 1. 5.08 divided by 3.39. 1.4985. Okay, so what do we do now? On the previous problem, we were done at this point because all 3 of those had magically turned into whole numbers. But these aren't. This is 1, 1, and 1 point. Would everybody say that's really close to 1.5?
Yes.
Yeah, okay. So 1, 1, and 1.5. How can I take those 3 numbers and get them all to be whole numbers? Okay,
Multiply them all by the same number.
which is
2.
2. Yeah. So if I see something like this and it's really close to a half, I can turn that into a 3 by multiplying by 2. And that's what we're going to do. The last step here is I'm going to multiply this times 2, multiply this times 2, and multiply this times 2. Okay, we're going to have 2, 3, and 2. Those will be my final answers. And my final empirical formula here, C2H3O2. Oh, looks like Cho 232. So my final answer here, 2, and 1.5 times 2 is 3, and 1 times 2 is 2. So my subscripts, these are my subscripts that end up being here. C2H3O2. Okay? Now, within reason, guys, here's where it gets tricky. Here's where it takes a little bit of judgment over here. Let's talk about this for a second. Suppose this wasn't close to 1.5. Suppose this was like 1.32. You might want to take a stab at what I'd want to do then. Okay.
Multiply it by 3.
Yeah, because that's really close to 3 1/3 or 1 1/3. Multiply by 3 and I'll get 4. If this is really, really close to 0.67, what's that? That's 2/3. I can also multiply that by 3. If this is really close to 0.25, I might want to multiply by 4, right? So if you find a number over here, use a little bit of judgment. We'll do another example in a minute, and we'll talk about that more, okay? If you look at these numbers, after you divide by the smallest one, you're going to say, is there one more step I need to do to get all whole numbers? Okay, page 981, I'm going to do problem or 2 from there. I'm going to do 2, let's see if we can. Nope, it's the wrong book. It's 981 in the other book. It's 876. There we go. 980, no, it is 981, 982. I like this one. Let's do number 31, page 982. It says beryl, B-E-R-Y-L. Beryl is one of my favorite stones. Beryl is a beautiful green stone. It's semi-precious. We get the word beryllium from it. Remember, sound familiar? B-E-R-Y-L. And when I was in high school, my wife gave me a little gift. It was a little green dragon, and I named him Jello. This is a green color. Anyways. Beryl is a hard mineral that occurs in a variety of colors. A 50-gram sample of beryl contains 2.52 grams of beryllium. This one's worded a little bit differently, so be careful here for a second. 2.52 grams of beryllium, Be. It contains 5.01 grams of aluminum. And it contains 15.68 grams of silicon. And it contains 26.79 grams, 26.79 grams of oxygen. Now it says there's a 50-gram sample here. There's two things you can do. You can do it the quick way or you can do it the slow way, okay? Who wants to do the slow way? Good, okay. If you wanted to, you could take these four numbers and you could calculate a percent composition. Right? Yes. Right? We could take 2.52 grams. We could add all these up and take 2.52 divided by the total and get a percent. 5.01 divided by the total and get a percent. 15.68 divided by the total and get a percent. You could do that. But what's the first step we're going to do? We're going to change them all back into grams anyways, right? So the very first thing they've given you, it says a 50-gram sample. What do I do with that? Nothing. Just ignore it, okay? You could figure out the percent composition, but we don't need to because we're just going to start with grams and change them all into moles anyways. So, step number one, change these into moles. Get your calculator out. We got grams of beryllium in 1 mole, grams of aluminum in 1 mole, grams of silicon in 1 mole, grams of oxygen in 1 mole. I know that one's 16, good. Silicon's like 30, 28, 29, 28.086. Aluminum here, our friend, 26.982. And beryllium is a real small guy, 9.012. And notice I'm not rounding these off in the middle here because I'm afraid when I get way over here on the right hand side of something that's so close to a half or 10.3 or something like that, that amount of difference might make a difference in this kind of calculation. So generally I do not round off. In some cases it might make a difference, some cases it won't. Bless you, twice. Okay, let's crank these numbers here. We got 2.52 divided by 9.012. I got 0.2796. I got 5.01 divided by 26.982. Notice there's a lot of calculator here. This is just dividing numbers though. Dividing and multiplying, guys. Okay? There's no scientific notation in these guys. 1857 or something like that. 15.68. 28.04. Right. Yeah, 15.68. 0.5592. And the last one here, 26.79 divided by 16. 1.674. Okay? Everybody cool? This is moles. You can put a heading at the top, or you can call them all moles. Moles of this, moles of that, moles of silicon, moles of oxygen. What's the next step? What do I do next? Michaela?
Divided by the smallest number.
Okay, what's the smallest number here?
0.1857.
Okay, so we're going to take the calculator again. Lots of crunching numbers here. 0.1857, that one's going to equal 1. And again, the goal here is to get at least one of them to equal 1. That's a whole number. Okay? 0.1857, 0.1857, 0.1857. I didn't do this problem last period either, so if anybody's watching, you might want to watch both classes, period 1 and period 2. 0.2796 divided by 0.1857 equals 1.5. Ooh, I like that. Okay. We're looking really close to 1.5. Mine says 1.505. This one, 0.5593, I think, divided by 0.1857. Ooh, that one's really close to 3. I get excited about this. When I see whole numbers pop up, right? Mine says 3.0118. I'm going to call that 3. Okay? And the last one here, 1.6743 divided by 0.1857. 9.016. I like what I'm seeing, so I'm going to round all these off, okay, because they're all within 1,000th of a whole number. And just like the other one, how do I get rid of that 1.5? Can't round him up. Multiply by 2, okay? So we're going to multiply this one by 2, multiply this one by 2, multiply this one by 2, multiply this one by 2. The ratio has to stay the same, so whatever we do to one of these numbers, divide by 0.1857, we have to do to all of them. Whatever we do over here, we have to do to all of them. Okay, so this is a 3, a 2, a 6, and an 18. So my formula, empirical formula is going to be beryllium, Be3, Al2, Si, 6O18. Now those numbers look big, but that's the right answer. Now I know something here that maybe you're not familiar with. There is a compound called silica, which is the main component in all sand. In fact, sand is SiO2. So I'm guessing that the real formula here, but I would accept this as the right answer, is Be3 Al2 SiO2 6. This is my guess. Again, I'm just showing you something because I know SiO2 is silicon dioxide, which is sand, and it's the main component of almost all minerals and gems and rocks for that matter. So this is your rocky portion, and your beryllium and aluminum are give different minerals their colors and their hardness and different things like that. So this is a really cool. Rocks are fascinating from a chemistry standpoint, by the way. Yes, sir.
How would that work?
What's that?
The SiO2 6.
Could be
6
times
12.
Oh, SiO3, which is a silicate. It's still a derivative of silicon dioxide, but it's a silicate. It's a polyatomic ion,
Do you have
Si3.
that?
No.
If you have to write on the test, which way would you?
No, you have no way of knowing this, so just ignore that. It's just for your information. Just give me this here, okay? Now, if you notice something that has PO4, phosphate, I did a problem first period, and we saw something NH3PO4. Wow, we know that. Sodium phosphate. If you see NO3, it's nitrate, right? So you can group things like that if you see something that you know that's a polyatomic ion. Okay, I got time for one more here. I want to do one of the ones with a molecular formula in it. So I'm going to do number 30, right on the same page, which is about eucalyptus leaves. One of the cool things about biology in today's world is we're still discovering all kinds of new drugs and helpful medicines that come from plants that are being discovered all over the world. Okay, so God gave us a planet with millions of different things on it, and if we can be smart enough to figure out them, we can solve a world of problems. So eucalyptus leaves are the food source for panda bears, and by the way, koalas, yeah. And eucalyptol is an oil found in these leaves. Everybody heard of CBD oil or cannabidiol? That's the big oil they take out of marijuana nowadays. But if you just extract the oil out of it, it doesn't get you high. It's supposedly it has a lot of health benefits if you take it or eat it or put it in your cooking and stuff like that. or just take pills of it. Everybody's advertising CBD oil, if you see that around town on billboards or even on ads on TV, okay? So you can extract oils from plants and leaves, and sometimes they have really cool effects on the body. Good, bad, or just hilarious. Okay? Analysis of eucalyptol indicates it has a molar mass of 154 grams per mole. Now, I'm going to put that number way over here, because I'm not going to use it till I get to the last step of this problem. That's the molecular mass, or molar mass, of the final answer. This one's not asking me for the empirical formula, it's asking me for the molecular formula. But it still starts the same way, 77.87% carbon. And so I'm going to start my problem, 77.87 grams. Mr. Debski, it says percent. Yes, but I know I'm going to change it into grams in a minute. So I'm going to save some board space here, and I'm going to just ignore the percent and change it to grams, because I assume a 100 gram sample, it's going to be in grams. And it's going to be 11.67 for oxygen, hydrogen. 76?
Yeah.
7-6.
I wrote it right, and I said it wrong, and I thought I said it right, but I wrote it wrong. You know what I mean? I went a little dyslexic there. 2.37 grams of oxygen, CHF. Here we go. Change them all to moles, right? First step, get your grams per mole on. 1 gram per mole hydrogen, 16 grams per mole oxygen. Notice I still say grams per mole even though I'm writing them upside down. Okay, get the old calculator out and crunch these numbers. Okay, 77.87. Oops, 77.87 divided by 12. Okay, I got 6.489. What do you got? 11.76 divided by 1. I always do that. I hate that. I don't have to do it. Anything divided by 1 is itself. I always catch myself after I punch it in the calculator. 10.37 divided by 16. 0.07. Is that right? No, that can't be right. 648. Okay, divide them all by what? 0.648. That's moles, by the way. Oops. Divide by 0.648. Divided by 0.648. Divided by 0.648. The bottom one's going to equal 1. Well, one of them always has to turn into 1. The top one, notice, is going to turn into 10. 6.48 divided by 0.648. Well, that's just moving a decimal place. And the one in the middle, I got to crunch on my calculator, 11.76. 11,000. 11.76 divided by 0.648. 18.15. Now, let's talk about this one for a second before I do anything else. And I only got about a minute. Do I do something with this? Okay, that's the question. My answer here is going to be if it's smaller than 0.25, most of the time you're not going to mess with it, okay? If I had to multiply 0.15 by something to get to a whole number, it would probably be 7 or 7.5 or 8, okay? And that's going to make this 70 or 80, and I will not give you any problems with that many atoms in there, okay? So this is a big molecule already. Our answer is C10H18O1. That's not the final answer. This is my empirical formula. And my last step is calculate the molar mass of this and compare it to that number up there. Okay? So 10 times 12, 120. 18 times 1, and 1 times 16 adds up to 154. Now listen, it turns out to be the same numbers up here. So in this case, the molecular formula is the same as the empirical formula. Give me 30 seconds. If this was 308, for instance, then I would compare this number to this number that was given in the problem, and I would say, oh, that's twice as big. and I would have to come and change all of these subscripts by a factor of 2 to get the molecular formula. Remember, your empirical formula times some number is always going to give you your molecular formula. Okay? Your homework assignment for tonight is not what's on the board over there. Please write this down. And period 1 made me leave that up there. I was about to erase it. This we're going to make this suffer, okay? So number 63, number 65, number 66, and number 68. I got one more for you, okay? And 161. 5 problems. They're all like this from chapter 10. Bring them with you on Monday. Please pass or leave your homework on your desk. I'll collect that in a minute. I want to take a look at those over the weekend and see how everybody's doing. You're dismissed. Sorry for keeping you long.
63, 65, 66.
Yep.